So math always seeks to quantify and model just about everything. So one of the greatest challenges is to try to quantify chance. And that's what our entire unit of probability does, is we try to quantify what chance is. Yes?
I got a great first question. What's the probability?
So with probability, we are attempting to assign a number to how likely an event is to occur. Terminology is extremely important. So here are some basic terms we have. First one is experiment. That's some process that occurs with well-defined outcomes. So like rolling a die is an experiment. Flipping a coin is an experiment. Rolling a die and flipping a coin would be an experiment. Outcome is a result from a single trial. So if I flip a coin, I get a heads. Heads is my outcome. Event is a collection of one or more outcomes. And then sample space, that is a collection of all outcomes of an experiment. So all the possible outcomes you could have by flipping a coin would be heads or tails. So your sample space would be heads or tails. So an experiment is run whereby a spinner is spun around a circle with 5 equal sectors that have all been marked off as shown. So we got 1, 2, 3, 4, 5. What is the experiment being done? Michael? Spinning the spinner. That is our experiment. Give one outcome of our experiment.
The spinner landed on 1.
Landing on 1. That is one outcome. Landing on 2 is an outcome. C, what is the probability of spinning the spinner and landing on an odd number? What is the event here? What outcomes fall into the event? So let's answer the question about the event. So the event is spinning the spinner and landing on an odd. So that is what our event is, to spin the spinner, landing on an odd number. What possible outcomes do we have for landing on an odd number? 1, 3, and 5. So now the probability of landing on an odd number, we have 3 odd numbers out of how many?
50%.
5. So we would either write it as 3 out of 5. Generally, probability is the fraction form. Sometimes they do use the decimal. So on some of my answers, you may see me writing both of them because they go back and forth. So it's either 3 over 5 or 0.6. No, not usually. So the answer from C helps us figure out the basic formula that we use to determine all probabilities. So the probability of an event happening is the number of that event, like we just did our number of odds, there were 3 of them, over the total number in the sample space, in which case that one above was 5, because there was 5 sectors that it could be out of.
So is it like part over whole?
Kind of, yeah. That's one way to think of it. So given the above definition, what 2 numbers must all probabilities lie? Between what 2 numbers? No. 0. This is what we call an impossible event. It ain't ever going to happen.
Ooh.
Yeah? 0 and 1. 1 is what we call a certain event. It will happen. Like, for example, it snowing in Syracuse is a certain event. It will always snow here. Even in the summer, it could snow here. You never know.
Yeah, I know sometimes it's crazy.
I'm not.
Let's not jinx us.
It has snowed on Mother's Day.
When's Mother's Day?
May.
It's April.
May is
Yeah.
Oh, we don't May
Okay, so when we are dealing with what we call theoretical probability, we don't actually have an experiment that's been done. We are working purely on theory. Like, for example, flipping a coin. Your theoretical probability is based on the fact that, it's got a heads and it's got a tails. You don't actually perform the experiment.
Oh, like the theory that the world is round?
Sure. So, exercise number 3. A fair coin is flipped 3 times and the result is noted each time. The sample space contains triples. Because you're flipping it 3 times, you have 3 potential outcomes, which would represent a head on the first toss, a head on the second toss, and a tail on the third toss. That's what this one represents here. That we flipped the heads, we flipped another head, and then we flipped the tail. Draw a tree diagram to show all the different outcomes in the sample space by flipping a coin 3 times. So first time I flip my coin, I could get a heads or a tails. So that line represents my first flip. So then if I get a heads on my first flip, what could I possibly get on my second flip? Heads or tails. And if I had tails the first time, I could get heads or tails the second time. So again, the second line represents your second coin flip. So, off of that heads, from my second flip, I could get heads or tails the third time. Off of the tails, I could get heads or tails. Off of this heads, I could get heads or tails. Off of that one, I could get heads or tails.
You know what? I think you get 2 heads in a row. Probability of getting a third head in a row.
It's still 1/2. What you get the first time around does not affect what you get the next time around. Okay. All right, B, list all the outcomes as ordered triples. How many outcomes are there? So for ordered triples, what they want you to actually write, for example, is 1 would be heads, heads, heads. Another one would be heads, heads, tails. We could get heads, tails, heads, heads, tails, tails. And I think that's all the combinations that start with a heads first. Right? So then we could get tails, 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 heads, tails, heads, tails, and tails, heads, heads.
We aren't going to have to do this, right?
Now, does it take into account, like, let's say the person broke their leg or something in the middle of the roll?
How does that affect their flipping of a coin if they broke a
broke
leg?
their finger on their both hands. And then he has to switch the finger that he flips it with. Exactly. So, ruining the rhythm.
How many outcomes do we have?
8. Give me more.
If we go over here and we count up the last row, we still have the same number of outcomes. We still have 8 outcomes. So whether you choose to do a tree diagram or list them out, you're still going to get the same number of outcomes as long as you do it correctly. So, part C, find the probability based on your answers from part A and B. We want the probability that all of the coins we flip are heads.
So,
So we got 1 out of 8. Probability that we have exactly 2 heads. Let's see here. This one has 2 heads. This one has 2 heads. That one has 2 heads. 3 out of 8. And then we have all heads or all tails. 2 out of 8. Now with probability, you don't have to reduce, but you can. It's not going to be wrong. So our 2 8s could be reduced down to 1/4. right, so sometimes we have to quantify chance by using observations, so you're actually using an experiment in that case. So that's what we refer to as empirical probability, because you actually have data in front of you that you're using, and then you're figuring out your probability based on that data. So my example here for that is we have a company was trying to figure out which one of their 3 sodas was the most popular. So they probably went to a grocery store, had cup A, B, and C, and told people, all right, try it and tell us which one you like most. So find the empirical probability that a person selected from random would prefer soda B. Express your answer as a fraction and a decimal accurate to 2 decimal places. So how many people like soda B? 24. Out of how many people total? 53. So there's our fraction. 24 out of 53. As a decimal, it would be 0.45. Well, yeah. No, because they said accurate to 2 decimal places. All right, B, find the empirical probability that a person selected at random would not prefer soda A.
So we add up B and C.
So you would add up B plus your C, still out of our total of 53. So that would give us 35 out of 53, which would be 0.66. All right, so sets and probabilities. A lot of times to try to help make our probability make a little bit more sense, we like to provide a graphical tool for it. So the graphical tool that we like to use is called a Venn diagram. Do you guys remember Venn diagram? You got a circle, and then you got another circle, and they usually overlap because they've got shared outcomes. So let's take a look at our first example. We have the set A is defined as the collection of all integers that are greater than 0 and less than 10. Does it include 0 and 10? No, because it's just greater than 0 and less than 10. So write out set A in roster form. So A equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Roster form just means you are writing a list. It's kind of like the roster for a sports team. It is just a list of everyone on the team. Roster form is a list of all the numbers. So show set A in Venn diagram form. This will be a very simple Venn diagram because we only have the one set, so you have just one circle. We label it as A because we are dealing with what we call set A. And then you just write all your numbers in there. One through 9.
Oh, I went to school. Tell me.
It's above 0, below 10.
I got excited.
A subset is any set whose elements are contained within another set. So give 2 possible rules that could be defined subsets of A, then write the sets as B and C in roster form. Do sets B and C have any elements in common? So for example, you could write all integers greater than 3. That would be an example of a subset from set A. So that would be like 4, 5, 6, 7, 8, 9. Yep, I just made it up. So another subset could be all even integers. That's another example of one. Would be 2, 4, 6, 8. You could do all odd integers. You could do multiples of 3. You could do multiples of 4. You can do the integers less than 7. There's a whole bunch of different ones you could come up with.
But these also take off A, so you can build up
So then they want to know, is there any common elements between B and C?
I got it.
What?
Oh, between B and C?
Yeah.
4, 6, 8.
4, 6, and 8 are the same, are the elements in both B and C. So let's go back to probability a little bit. So consider an experiment where we first toss a coin, note the outcome, and then we roll a 6-sided die, and we note the outcome for that one. Write a set of ordered pairs, such as, for example, H comma 4, which would represent heads, and then a 4. That represents all outcomes of this experiment. Remember, we call this our sample space when you write out all the possible outcomes. So let's start. We could flip a heads and then roll a 1. We could do a heads and then a 2. Heads and then a 3. Heads and then a 4. Heads and then a 5, and then heads and a 6. And that's all the ones that start with heads. So then we got all the tails. Tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. I think so. So in B, they want us to write a set of ordered pairs that represents the event of getting a tail and an even number. And we're going to call this set A. So A equals tail and an even number. So tail and 2. Tail and an even number. Tail and 4. Tail and 6. All right, C, the complement of set A will be all of the elements in the sample space that do not fall into set A. Write out the complement of set A. We're going to call this set B. So B equals, and it's everything from here that we did not use for part B. So that would be all the ones that start with heads. So heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, and then which one from tails did we not use?
Tail 1, 3, 5.
Tails 1, tails 3, tails 5. So that is our complement. Again, that was everything that was not used for set A. So next in D, they want us to find the probability of set A. So again, just reviewing that definition of probability, it's the number of elements in set A over the total number of elements in the whole sample space. So how many elements did we have in set A? 3. 1, 2, 3. How many groups did we have in the sample space? 12. Count them up. We had 12 ordered pairs there in our original sample space. So 3 out of 12 or 1/4. So the probability of getting A would be 1/4. The probability of B, again, is the number in set B over the number in the sample space. So how many groupings did we have in B? 9 out of the whole 12 in the sample space. So that gives us 3/4. What would happen if I added these together?
You
You get one whole. Any event and its complement is always going to equal 1. because it's definitely going to happen. If you take something and it's the opposite of it, it's always going to happen. So a set and its complement are important when we look at probability because all outcomes fall either into that event or into its complement, but it can't fall into both at the same time. Different textbooks use different notations for your complements, so we're not really going to use a notation for it because there's so many. Some people use a squiggle, some people use a little C to represent complement. It's just easier to use words instead of symbols. So we're going to consider rolling a 6-sided die and recording the result. Let set A be the event of rolling a number greater than 4 and B be the complement of set A. So we're going to draw a Venn diagram to represent this. Now, since these are complements, the two circles in our Venn diagram representing set A and set B are not going to overlap because they're not going to have anything in common. They're complements. They're basically opposites of each other. So set A are the numbers greater than 4. So on a die, what are the numbers greater than 4? 5 and 6. So A is just the numbers 5 and 6. B is the complement of that. So what's going to be in B? 1, 2, 3, 4. There we go. There's our Venn diagram to show that. So over here, find the probability of A. What's the probability of getting a number from A out of 6? Which would be 1/3. Probability of B, 4 out of, which is 2/3. So in part C, what is true of the sum of A plus B, 1/3 plus 2/3 would equal 1 whole. So what's true of the sum of P of A plus P of B, probability of A plus probability of B, is that it equals 1. Yep, complements when added together will always be 1. So then they want us to prove that the sum of the probability of an event with the probability of its complement will always be 1. So we're trying to prove that the probability of A plus the probability of not A is going to be 1. We're going to call it not A for now. Because it's not always called B. We've been using B. So the probability of A is the number in A over the number in the sample space. So the probability of not A would be the sample space minus what's in A over the number in the sample space. I mean, that's basically how we figure it out. Yeah, we've been able to look at it, and you don't realize that's what you're doing to figure it out, but you're taking however many are in the sample space, subtracting what was in set A to get you your complement. That's an S. So then what happens when I take this and I add it to the negative version? They cancel, so we're left with the number in the sample space over the number in the sample space, which is a 1. So it's always going to be true that an event and its complement are always going to equal 1 if you add their probabilities together. So we actually use this concept a lot without even realizing it. So if we look at example 4, we're going to answer these questions using that theory there. If the probability I draw a red marble from a bag is 3 out of 17, what's the probability that I will not draw a red marble out of the bag? Not 4 out of 7. Yes, you got to take 1 whole, subtract the probability of getting the red. Yes, you did. And we get 14 out of 17, which is its complement. Part B, if the probability that it will rain tomorrow is 20%, what is the probability it will not rain tomorrow? But again, we would move our decimal over, use the decimal form of it. Without realizing it, this is what you're doing, is 1 minus your 0.20, or 80%. That rule is used quite a bit. So in theoretical probability calculations, the set that makes up the sample spaces can get difficult to write out. It's good to remember things like tree diagrams to try to help you. So they want us to draw a tree diagram to represent the sample space of rolling 2 4-sided die. And they want us to figure out how many outcomes are there going to be. So if I roll the first one, I can get a 1, a 2, a 3, or a 4 from rolling my first 4-sided die. So after I roll that first one, I roll my second 4-sided die, and what could I get on that one? A 1, a 2, a 3, or a 4. So if I rolled a 1 the first time, I could get a 1, 2, 3, 4 again. If I roll a 2 the first time, I can get a 1, 2, 3, 4 the second time. If I roll a 3 the first time, 1, 2, 3, 4 the second time. And same thing with that 4. I can roll 1, 2, 3, 4 the second time. So how many outcomes do we have total? No.
Wait, no. 8,
16. A quicker way to figure that out, if you're ever trying to figure out how many outcomes you have without having to draw a tree diagram.
Like it is 4-sided.
It doesn't always work that way. You have 4 possible outcomes when you roll the first die, times the 4 possible outcomes when you roll the second die. It just happens that they're both 4s this time. That's how you'd get 16. If I was flipping a coin and then rolling a 6-sided die, so coin and a die, it'd be 2 times 6. There would be 12 total outcomes for that one. So you just multiply how many outcomes on one times the number of outcomes on the other one. No, that's always true. If you're trying to figure out how many objects are in your sample space, you just multiply your total number of outcomes. So then over here, what is the probability that you don't get 2 of the same number? Well, if I roll a 1, any of those ones would fulfill it if I got a 2, 3, 4 afterwards. For a 2, if I got a 1 and then a 3 or 4 afterwards would work. 3 and then a 2, 1, 2, 4. And then for the 4, the 1, 2, 3. So how many of those would work? No. 12. You got 3, 6, 9, 12 out of 16. Which would reduce to